Right, so here it says here to for the reaction below to predict the major elimination product. And I do want to mention here that you are just being shown what the substitution product is. So with that in mind, what was the nucleophile with the substitution product? What did I show? It was methanol. Yep. So if you're ever concerned on if you're being shown the substitution product here, just whatever the new group is, that was your nucleophile. So we see here that the CH3O that probably came from methanol. With that in mind, we're going to need a base to get the elimination product. We can show either water or methanol doing it. I would accept either one because they're roughly equal strength. But typically what you want to do is if you're trying to figure out what the base is, think about everything that's in solution and what the strongest base would be, and then use that as your base. So with that in mind, let's go ahead and take a look. So we have, do some arrows here for the major product. Okay. So the first thing you want to do here is recognize that we have HCl and water. Those two react to make hydronium, H3O+. And I believe I was showing that in lab actually as what phosphoric acid and water. I think we used as an example. I think we also used HCl and water at some point in there. In all of these mechanisms, you want to start off with protonating an oxygen if we have one available. So here I'm just going to draw out the hydronium ion. And let's use purple today. So there. And what is the reason of protonation here again? You guys remember? What was that? Yeah, make it a good leaving group. Okay. So next step here, what do we do? Yep, remove the OH group, so that is now a good leaving group. We should go ahead and show that leave. And then we generate a carbocation. Has the rate determining step been shown yet? Yep, that is the step we just showed. The question is asking you to specify what the RDS is. That was rate determining step. That's your slow step that is determining your reaction kinetics. That is the step that we just did. So whenever the leaving group leaves, whether it's SN1 or E1, that's what we get. Okay. So the next thing that happens here is we have an H1 carbon away. You can go ahead and show a hydride shift. This is a fast step, so that's not going to determine your rate. That step already happened. And the motivation or the driving force behind this is that we're going to get a more stable ring structure. A more stable carbocation. So it went from being secondary to being tertiary. And whether you're doing SN1 or E1, the reaction is identical up to this point. So if we wanted to get to the substitution product that is shown, I would now have methanol attack this carbon, and then it should lead to this product. But the question is asking for elimination. So what you want to do then is take a look at all the H's that are next door. So I'm going to go ahead and draw them all out. So this one carbon away has 3 H's. This carbon here has 2 H's, and then this carbon over here has 2 H's as well. The carbons on the left and the right are equivalent, so it doesn't really matter which one I choose on those ones. But then with the one in here on the top here is different. When you're first figuring this stuff out, I do recommend that you draw all the possible products and then try to figure out what major and minor and all that kind of stuff is. All right, so let's go ahead and label these. So let's go ahead and call these the ones and then twos. So I want to draw it, if the base were to grab the H at 1 here, it would give us this product. If it grabbed one of the H's that are at the 2 here, it's going to give us this product here. So once again here, you shouldn't have to, after you have enough practice, you shouldn't have to draw all these out. But you want to think about, okay, it can eliminate here, here, or here. And then which one's the most stable product? You also have to consider the size of your base that you're using.
The right one?
The right one is major, and why is that major?
Because it's tertiary.
Well, it's more substituted. So we say tri-substituted here, and so now we know which one's major is this one here. I want to go ahead and show the actual mechanism leading to the major product here with the arrows. So grab the H, that's going to lead to the more substituted alkene, which is the major product. And what was the other name we used for that? For more substituted? Was Zastev product. Yep, that's Zastev. Okay, and this one here is minor. And what was the name for the minor product? The Hoffman product, yep. Okay, I want to, because of what the next question is asking us, I want to go ahead and show what the other product is by mass balance. So here we're showing a water molecule picking up an H acting as a base. The conjugate acid of H2O is hydronium, so we get that. And the next question is asking you, what is the role of HCl and H2O in the reaction? And we kind of did show that in the mechanism. You guys see it? It's a catalyst, yep. So whenever we have a reaction that has a catalyst in it, you want to show it being used and then being remade. That way you know you have the correct mechanism there. Because if you're not showing your catalyst being used in some way, what was the point of adding it? There is no point of adding it unless it actually allows a different reaction to occur. And then energetically, what is the point of the catalyst again? It speeds up the reaction how? It lowers activation energy, yes. So and that is directly related to how easy this group can leave. So if this group were to leave right now, it would lead as an OH minus, which is a strong base. That would have a huge activation energy, where if it leaves as a weak base, that has a much lower activation energy. So you are technically adding an extra step in this mechanism, but overall lower energy of activation. That is the whole point of the catalyst. They typically have more steps involved. You know, an organic reaction they can have just a handful of extra steps, where a biological reaction may have 30 extra steps just to get the lower energy overall. All right, so kind of going back here. So I think the trick in this question was to recognize that we did have a rearrangement, but it really had no consequence on what the product would have ended up being. Because either way, it would have eliminated over here to give us a more substituted product.
So why were we shown the substitution product? Just to throw us off? What was the point?
Why not?
Which one was the file?
That like totally threw me off, and like when I first tried to do this problem.
It shouldn't have. You could have just put your hand over it. All right. You guys want to work on a different one? Anyone in particular?
Just in the front, that was the E2 reaction, right?
E1. E1. Yep, so if you're showing a carbocation, that's always monomolecular. So that's either E1 or SN1. If you don't have a carbocation, that's SN2 or E2. All right. So you guys want to just pick myself, or do you guys want to work on one in particular? Have you guys been working through this stuff at all? 15, you said? Okay, that was the one I was helping one of your classmates with earlier. Okay. So it says here the trans product shown is the only observed product of the reaction. Provide a mechanistic explanation as to why none of the cis product forms. You do not need to show transition states. So the thing about this kind of question is trying to get you guys all the chiral centers that are happening here. Notice there are 2 chiral centers there. This is similar to what we did in class last time. So I think the best way to approach this is to figure out whether or not it is E1 or E2 here. So we're going to look at a elimination product. Based off of the substrate, what is the substrate? That primary, secondary, tertiary.
Secondary?
It's tertiary. Yep. There's carbon, carbon, carbon. So this thing is tertiary. So let's use red. So it's tertiary. Is there anything else special about the position of it?
It's whatever. Well, the H is over here in the VR.
Well, I'm not really worried about conformation. I mean, I'm thinking like the position, the carbon position it's in. Is that it's one away from the ring? What do we call that? It's benzylic, yes. And the reason why that's significant is because if you form a carbocation in the benzylic position, they end up being resonance stabilized. So they can go SN1 or E1 if they want to. So is this information telling us anything about whether it's E2 or E1? So the question I have for you guys, so just ignoring substitution, only looking at eliminations here, does tertiary have an impact whether it's monomolecular or bimolecular? So it actually doesn't. So the reason why is because you're attacking one carbon away. The main reason why SN2s were restricted by tertiary is because of the backside attack. We don't have a backside attack with E2. It's going to instead attack one carbon away. It's going to attack one of these one, that one, or this one. So my point here is that tertiary can undergo E2 just fine. So that's not really limiting here. I would argue that we're probably going to get an E2 because I would go to the next thing would be the base here. So I believe what's going to happen here is that we're going to see that the product here with probably major going to be trans. And to get to the other product, you probably have to do an E1 instead. But we'll see. I'm just jumping the gun here a little bit. I'm going to start off by Newman projection down that way. So what I'm going to do is draw the Newman projection. I want to get the H, this H right here. I want to circle it. So I want the H and the BR to be anti to each other. I believe right now they are this is actually in an eclipse conformation the way that it's drawn. So I'm going to go ahead and draw this. So ET, left would be the H, right would be methyl. And then in the back here we have a pH, and then bromine. Remember, pH stands for phenyl, so your benzene ring. And then we have our methyl coming down to the left. Okay, so I'm just going to pick one. I'm going to go ahead and pick the front carbon to rotate. So it looks like if I rotate the front carbon 60 degrees clockwise, I will make the H and the bromine anti to each other. So the H that we're looking at is that one, and I'm going to rotate it such that it is in that position. And it'll now be staggered. All right, so H that way, ET is now this way, methyl is down, and then the back carbon did not change. So pH, BR, and then CH3 did not move either. Okay. So looking at the carbon structure here, H here and bromine are going to eliminate. And we're kind of looking at the alkene from the side. So recall that alkene's geometry is trigonal planar, they're flat. So you can imagine here that we're basically cutting out the middle here. So this part's going to eliminate. And then we're seeing which side the groups are going to land on in the alkene. So the alkene is going to be right here in the middle between them. Looking at this drawing here, the most stable conformation here for an E2 is going to put phenyl and ethyl on the same side. So I'm going to go ahead and draw that. So ethyl, here is our double bond, phenyl is that way. So here's your front carbon, here's the back carbon, and then it looks like we're showing two methyls going in the same directions. Okay.
Why is the phenyl and the ethyl switched? See how
Compared to what it should have been, right? So you're thinking compared to this one? So this tells me that in the only way that we would have been able to get to this product, it could not have been an E2 elimination. It had to have been E1. So here, E2 gives V only. The mechanism had to have been E1. That's your explanation. Recall that E1, because we have the carbocation intermediate, we don't have this restriction of the things having to be antis to each other. So it turns out where the more stable alkene will always form via E1. So in order to get this particular isomer, it had to have been E1. If you weren't given this product though, just based off what's shown there, I would argue that that's probably going to be an E2. And the reason why is the base that's being used. But this is here is just illustrating the possibility that it can be both. All right. Next question here is predict the major product if the conditions of the reaction are changed to potassium terbutoxide and tert-butyl alcohol solvent. So basically it's asking you to predict the Hoffman product now. So how did I know that it's asking for the Hoffman product? I'm the teacher, is that why? Or
Cheater.
I'm cheating. I have the answers over here. It's because you have a bulky base. So bulky bases give less substituted products. So bulky base give less substituted product, and the name we used for that was Hoffman. So I got a question for you. Those of you guys that are following the handbook, do they spell with one F or two Fs? I've seen it spelled both ways actually. So I'm wondering like how does this guy really spell his name? Because I've seen some books have it with one F, some have it with two. So I guess the workbook had it with two Fs. I learned it with two Fs here. So you got a question?
Yeah, how do you know if it's a bulky base?
If it has large groups on it.
Oh, so just any large group?
Yeah, typically they're branched groups.
Okay.
So let me show you some examples of bulky bases. The two that I gave you guys in class were that is a bulky base. This is actually the one that's mentioned, potassium terbutoxide. The other one was LDA. These are both bulky bases. That was Li plus. This was LDA for short. Some branch groups, if you have the conjugate base of isopropyl alcohol, that is also a bulky base. And essentially the thing is branch groups make it bulky. And the reason why that's significant is because it's going to grab the H's that are easier to get at. So what I mean by that is going back to this question here. Whenever you look at these products, you want to think about, okay, which one carbon away where the H is at. So this one has an H here, and then over to the left there's the H. That was how we got these two products. So essentially what it's asking you to do now is to eliminate here. So I want to go ahead and draw that product. So we got our benzene ring. That is our new double bond. And the rest is kind of just sitting there. And then methyl that. All right, so this is separate. Now we need to worry about stereochemistry, right? On this carbon. So I believe it should be a wedge or a dash on the methyl. Should be a fun one. All right, so this has 1, 2, 3. It's R. This one has 1, 2, 3. R. Should be a wedge. Okay. Question on this one? This what you guys got on your own, doing your homework? All right. I want to go ahead and back up a little bit to the same page. The question here is number 14, the one on the top of the page here. This is actually pretty normal for multiple choice that typically asks for E2, SN2 type stuff. So it's asking you to predict the major products. So a couple things you need to consider here. So we had that situation last time where I was showing you the ring structures. In order for the H and the bromine to be able to become anti to each other, they have to be trans, right? So noticing this compound right here, this CH3 is trans to the bromine, where the H here that would lead to the more substituted products are on the same side. So instead, it's going to grab one of the H's on this carbon. So it's going to be less substituted product here. So which one is that for elimination? It's a C or D. It is choice D is less substituted. I know it's kind of drawn these weird sort of chair conformations, but we can see that it's less substituted here. This one is more substituted. Once again, this cannot form because of the orientation of the bromine and the H. These must be anti, which means they must be trans to each other. All right, next one here, SN2. SN2 has inversion of stereochemistry. So if you're looking at the chair conformation, if it's pointing downward, the new group should be upward if you had an inversion of stereochemistry. So that means that the OH should be up. And that means methyl should be up also. So the point here is that OH and methyl must be cis to each other, which is choice B. So B and D are the correct answers here. All right.
The H and the BR, are they not on the same axial thing? What?
You talking about, which H are you talking about?
Yeah, that one.
This one?
Yeah.
It's on the same carbon though. It eliminates one carbon away. So when it grabs that, when the base grabs the H, it's going to grab from one carbon away. So this is not even going to be part of the mechanism at all. Only this one or this one. It's the same kind of thing we were doing down here. So down here I was saying one carbon away, H.
I'm just confused by the drawing.
Yeah, that's probably what it is. So you still need to follow the rules like to the letter though. It's one carbon away. So you could go ahead and just label them.
Actual position? Is that what I'm saying? Not that H.
So it's going to be an H's on one of those two carbons are the ones that are
And the
possible
BR
to
is
eliminate.
not axial position? Yeah, okay, it's just showing them both, yeah.
Well, technically the way that drawing is, BR is currently equatorial.
That's,
So you could draw a proper chair here that might help with this a little bit better. So let me fix the chair drawing here. Maybe it'll make it a little bit more obvious what's going on. And you guys love these chair conformations. No. All right, so I like to draw these going left to right. I think it's a little bit more obvious. This one's kind of at an angle. Based off the drawing here, it looks like methyl is here, and then H should be straight down. This one has H up, and then bromine is coming down like that.
thank you.
So that's probably what's throwing you off there, is the way that drawing is. The H that we're looking at that's going to eliminate is on the next carbon. It's going to be the one that's pointing upward here, equatorial. But we can do a chair flip. And this was going like that. Okay, so methyl here is now up. So this is actually a better drawing to look at it from. Because now the bromine is axial where we want it to be. So now we see this drawing here, it's going to selectively grab this H, which is, in comparing the drawings, is that H. All right. Are there other questions about this one?
Can you repeat what you said about the alcohol and the methyl must be what in the product?
Oh, so the if you're looking at the inversion here, so from the chair conformation, so in order for you to have an actual inversion here, here we have bromine coming down. That means the OH must be going up. And then I was looking at the orientation of where the OH would be relative to the methyl group. Because the methyl's not even involved in the reaction at all, so it's not going to move. So they should both be upward. So they're cis to each other. Yeah. A situation that you could potentially see on a standardized test would be where they may have given you the chair conformation here, and then you had flat drawings here for your choices. Or you could have had a flat drawing here, and then chair conformations for choices. That is potential for exam stuff. We'll see. All right, I want to go ahead and, these are good ones. Were there any in particular you want me to work on? I just want to mention here, if you want to do more practice on what we were just talking about, number 4 is good for that. So this one's going to give you a less substituted product. But I'll let you guys figure that one out. I wanted to point out that number 7 is literally the same question we just did. This is what I was talking about, that you could be given flat versions. This is actually the same exact question. Just the structures are changed a little bit. But it's literally the exact same compound, the same things here, the same choices. Just now one's drawn flat, one's drawn in the chairs. So same kind of thing again. I want to take a look at number 8. Just so you guys are clear about what is happening with the Newman projection stuff here. It says here to draw a box around the major product. We could do that first. Which one is the major product, the left one or the right one? The left one here. So this one is major. I was asking you to draw a box, so we can go ahead and follow the directions here. Just draw a box. Oh, a little funny topic here or mention here. You may notice here that I use a lot of boxes in my activities. And I used to have this running joke when I taught OCHEM where I would say, I don't think I set the box, so I only grade what's in the box. And that was a way to make it really clear what I was grading. I don't do that as much anymore, but when I first started teaching, I was trying to keep my grading under control, and that's how I did it. I only graded inside the box. So if it's not in the box, I didn't grade it. All right, so here we don't have the issue with the other ones that we had. This one here, the main thing is to consider is cis versus strands. And the reason why is because there's 2 H's on this carbon here. If you have a choice between which H it can grab, it's going to selectively give you the one that's going to lead to the more stable product. We can see that with Newman projections. And I want to go ahead and do that. So just we have plenty of practice with using Newman projections to predict what's happening here. I know a lot of textbooks do not do this Newman projection approach, but I like it because you guys really understand it after we're through it. Okay, so looking at the Newman projection here, so coming upward, we have an ethyl, and let's just label this as methyl, and then there's 2 H's. Okay. So right now it's already in the conformation where H and bromine are anti to each other, like that. Another possibility where I were to rotate it such that the other H is in that position, and I'm going to do that. Go ahead and do that, and leave the front one alone. And I do realize the question is asking for a mechanism, but I want to work on this instead. Oops. Sorry, we're going to rotate the back one with the front one alone. So this is H, B, R, M, E. Rotate the back one. The H is here. The other H is now up here. Ethyl is now here. And just like before, the elimination is going to happen with these 2. So you could just draw the mechanism. There's actually plenty of room to do that up here. It's literally just 2 steps, or 2 arrows, sorry, 3 arrows, that. But looking at the Newmans, which one led to the major product? The left one or the right one? The left one is more stable, and it's leading to the major product. So here we see the ethyls are opposite directions. That's what happened in the product. So here we have our methyl here, ethyl here, pointing in opposite directions. Here we're seeing methyl and ethyl pointing in relatively the same direction, and that's the minor product. So in this case, nature can make a choice now which one it's going to go for. It's going to lead to the one that is the more stable product, which is the trans one. So in questions like this, you're typically don't have to do Newmans because of that. To question like number 9, you probably might have to do that. So let's do it. So next question here, I'm kind of being nice and telling you specifically that it's SN2 and E2. And what is the giveaway? If you guys did not have these labeled, how would you know that? DMSO, but there was something that came up before that. So what was the order again? We go substrate,
Strong base.
then nucleophile / base. So this one is not telling me anything because it's secondary, so that could be monomolecular or bimolecular, but next thing is we have a strong nucleophile / base. This is going to be second order. And then if you had to go further on past that, we have DMSO there, which is a polar aprotic solvent, which leads towards the second order reactions also. Where if this was in just methanol, that would lean more towards the monomolecular ones. All right, so here, using proper arrow formalism, draw the mechanism of each. And then I mentioned here, make sure to include relevant transition states for both mechanisms. So let's do it. Yay. All right, so I'm just redrawing this here. And we're going to try to avoid some mistakes I have seen students make. So one of the first things you might think of with SN2 is that you have an inversion of stereochemistry, and the thing is that it's only the stereochemistry that's involved in the reaction. So this chiral center is not involved in the reaction. Don't change the stereochemistry on it because it didn't do anything. So we're only going to be worrying about the other one. So NaOCH3. So you show your backside attack. That. Kick out the leaving group. Before I do the transition state though, I like to go ahead and just draw the product and then come back to the transition state. Remember, the transition state is the in-between of the reactant and the product. So it makes sense to have them both drawn already before you do that. So leave a little space in the middle and then draw the product. To quickly give you the product, all you got to do is flip stereochemistry on that one carbon to give us that product. And the transition state now is the main carbon chain is not doing anything. Neither is that carbon. So I'm going to use red here for the partial bonds. These are the bonds that are new bond forming, bond breaking, And that is with OCH3 is incoming, BR is leaving. Don't forget the brackets, double dagger, and then partial charges, right? So partial charges is full negative is becoming neutral. The in-between is delta minus, and then neutral becoming full negative because of the leaving group, delta minus. And just for the sake of fun here, I want to include the additional products here for mass balance. What else should I include then? Sodium bromide. Yep. So here's a Gen Chem question for you. running this reaction in DMSO, would you have a precipitate of sodium bromide?
Maybe?
You would.
Because it doesn't.
Yeah. That if it was in water, it would dissolve, but if it's an organic solvent, it's going to stay. Like dissolves like. I should give you guys my 103 test tomorrow and see how you do. It's all stoichiometry. Oh no. Based on what we saw a few weeks ago in lab, I'm not sure how well you guys would do. All right, this one here, you might notice I have a sort of a liking for the stereochemistry ones here, where both are chiral. So maybe use that as a little hint on what to expect on the test. So what do you guys think for this one? I'm thinking that since they're both chiral, just draw a Newman projection and use that to predict. So I want to do that first before I do anything. So I'm actually going to get a separate sheet of paper here because I don't have enough room for that and the mechanism. So I'm going to draw the Newman projection looking down this way. And the reason why I'm recognizing to do that is because of the fact that we have two chiral centers involved to give us the Zaystep product. Whenever you have that situation, I would just draw the Newman. And with someone like me writing tests for you guys, I'm probably trying to trick you guys with the stereochem thing. So, all right, so it looks like the methyl and the bromine are currently anti to each other. And ethyl is coming down, and the H that we want to eliminate now is currently gouged to the bromine. So in order to get that in the right position, I'm going to grab that one and rotate it all the way over here. And then use that to predict my product. So front carbon, nothing changed, rotated the back one. Back one has an H here now, methyl is down, ET is over here. And we are going to eliminate this one out. So we can then see that we have ETs in the same direction, H and ME in the other direction. So I'm going to draw what that product would look like and then go with that to draw my mechanism. So ET, same direction, double bond here. Let me get rid of stupid Norton. All right, and then front carbon has an H, back carbon has a methyl. All right, so this one is giving us the cis product. Come on, like that. Okay. So let's do the mechanism now. Now that I correctly predicted the product. All right, so bromine here, I'm going to leave that carbon alone. And I want to rotate this a little bit, just like we did in our structure here. So I'm going to go ahead and have methyl down. So basically what I'm going to be doing is rotating this such that this H is anti to the bromine. Same thing we did in the Newman projection. So I believe by doing that, we now have ethyl this way. All right, and then now we can go ahead and draw the mechanism. So same mechanism here. This is going to grab the H, double bond, kick out the leaving group. And we don't want to jump the gun yet. I don't want to draw the transition state yet until I get the final product, which is that. All right. So this part here, this bond is breaking to bromine. Sigma bond didn't do anything. This bond to H is breaking. Oops. We're getting a new bond in between, like that. And then the other things are not doing anything. They're just kind of there. Like that. Not quite done yet. We have to add a few things. So the base is part of this. So the OCH3, that's getting a new bond to H. And then we don't forget our double dagger. Partial charges should be similar here. Bromine is leaving, delta minus. OCH3, it's going to be delta minus also because it's going to be neutral as a methanol after. There we go. Recall that when we first went over transition states, I mentioned then that transition states are not unique to SN2s. They are literally every reaction in the universe have transition states. They're any in between in a mechanism step. They're typically just talked about during SN2 though. And the main reason why we talk about it then, is, from my understanding, is just that we put an emphasis on the inversion of the stereochemistry. You kind of see that clearly in the transition state. All right. So let me stop this here.